What if I told you that the universe is controlled by four fundamental forces? This isn't a plot twist from a science fiction novel, but the reality of our cosmos. These forces, electromagnetism, gravity, the strong nuclear force, and the weak nuclear force, are the silent puppeteers choreographing the dance of every particle in the universe. Electromagnetism, for instance, is the reason why you're not falling through your chair right now. It's the force that holds electrons in their atomic orbits, lighting up our world, powering our devices, and even governing the chemical reactions in our bodies. Gravity, on the other hand, is the quiet maestro of large-scale structures. It's the reason why we're grounded to the Earth and why our planet orbits the Sun. It's the force that sculpts galaxies and dictates the cosmic ballet of celestial bodies. But let's go smaller, to the core of matter itself. Here, the strong nuclear force takes over. It's what glues protons and neutrons together in the nucleus of an atom, overcoming their mutual repulsion, and it's the powerhouse behind the sun and other stars. Then there's the weak nuclear force, the odd one out, responsible for radioactive decay and nuclear fission. It's a key player in the nuclear reactions that fuel the sun, and it even has a hand in our very existence, contributing to the formation of elements in the aftermath of the Big Bang. These four fundamental forces shape everything we see around us, from the tiniest particles to the largest galaxies. They are the building blocks of our universe, and to understand them, we delve into the fascinating world of quantum field theory. It's here that we encounter the Yang-Mills theory, a cornerstone of our understanding of these forces. This theory, named after physicists Chen-Ning Yang and Robert Mills, is a remarkable piece of the puzzle that brings us closer to unifying these four fundamental forces. So let's embark on this journey together, as we unravel the intriguing world of Yang-Mills theory and its role in the grand scheme of the cosmos. To understand these forces, we delve into the fascinating world of quantum field theory, where the Yang-Mills theory takes the center stage. In the 1950s, two physicists, Chen-Ning Yang and Robert Mills, developed a theory that revolutionized our understanding of fundamental forces. This theory, now known as the Yang-Mills theory, is a cornerstone of quantum field theory, which is our best description of the fundamental forces of nature. Let's peel back the layers of this intriguing theory. At its heart, the Yang-Mills theory describes what we call gauge fields. Now, these aren't your typical fields associated with particles. No, these are force fields that govern the interactions between particles. And the mediators of these interactions? Those would be the particles we call gauge bosons. To bring this into sharper focus, let's consider a familiar example, the photon. Photons are the gauge bosons of the electromagnetic force. They mediate interactions between electrically charged particles, like electrons, and are responsible for the force of electromagnetism. Now, an important feature of the Yang-Mills theory is something called gauge invariance. This principle asserts that the equations of the theory remain consistent, no matter what mathematical transformations are applied. In other words, the theory looks the same from any perspective. This is a crucial aspect of the theory, as it maintains a balance, a unity, between particles and forces. However, the Yang-Mills theory sparked a conundrum. If gauge fields and their corresponding bosons are the mediators of fundamental forces, then how do these gauge bosons acquire mass? After all, we know that some gauge bosons, like the W and Z bosons of the weak nuclear force, do have mass. This was the puzzle that the physics world needed to solve. But the Yang-Mills theory posed a question. How do gauge bosons acquire mass? This question would lead to a new theory, a new understanding, and a new particle. But that, dear listeners, is a story for another scene. According to Goldstone's theorem, gauge bosons should be massless, but that's not what we observe in reality. Now that's a head-scratcher, isn't it? Let's take a closer look. Goldstone's theorem, named after physicist Jeffrey Goldstone, is a fundamental concept in quantum field theory. It states that if a continuous symmetry of a system is spontaneously broken, then there should exist massless particles. These are known as Goldstone bosons. In the context of Yang-Mills theory, this theorem suggests that gauge bosons, the particles that mediate the fundamental forces, should be massless. But here's where the plot thickens. When we look around, we find that some gauge bosons, like the W and Z bosons of the weak nuclear force, do have mass. So how do we reconcile this contradiction? This is where the concept of Goldstone states comes in. These states would be particles with zero spin, emerging in the absence of mass for gauge bosons. But again, the reality we observe is different. Gauge bosons like the photon, W and Z bosons, have spin 1 and non-zero masses. So we're left with a paradox. On one hand, we have Goldstone's theorem telling us that gauge bosons should be massless. On the other hand, we see that some gauge bosons do have mass. This contradiction is the heart of the mass-gauge boson dilemma. But as it often happens in the world of physics, a problem also presents an opportunity for a breakthrough. This discrepancy between Goldstone's theorem and the observed reality led to physicists scratching their heads, pushing the boundaries of their understanding, and eventually, the development of a groundbreaking theory, the theory of spontaneous symmetry breaking. This theory, as we'll discuss in the next scene, not only provided a solution to the gauge boson mass problem, but also predicted the existence of a new particle, the Higgs boson, that would revolutionize our understanding of the universe. But that's a story for another scene. For now, let's bask in the intrigue of this fascinating dilemma. This discrepancy led to the development of a groundbreaking theory, the theory of spontaneous symmetry breaking. Physicists Englert, Brout, and Higgs proposed a solution to the puzzle of gauge boson mass. They introduced a concept that was as mind-bending as it was revolutionary, the theory of spontaneous symmetry breaking. Imagine a perfectly symmetrical object, like a pencil standing straight up. It's in equilibrium, but it's unstable. Give it a nudge and it falls. But in which direction will it fall? That's unpredictable. It's spontaneous. The symmetry of the upright pencil is broken when it falls, but the laws of physics remain the same regardless of the direction it chose. That's the basic idea of spontaneous symmetry breaking. Now let's apply this to the realm of particle physics. Englert, Brout, and Higgs proposed that a similar spontaneous symmetry breaking occurs in the quantum field. They suggested the existence of an all-pervading field throughout the universe known as the Higgs field. Just like our pencil, this field is symmetrical and in a state of unstable equilibrium. When particles interact with this field, the symmetry is spontaneously broken. This interaction is what gives particles their mass. The more a particle interacts with the Higgs field, the more mass it has. Gauge bosons, like photons, don't interact with the Higgs field and therefore remain massless, preserving their speed of light pace. But how do we know this field exists? Here's where our friend the Higgs boson comes in. The Higgs boson is like the messenger of the Higgs field. It's the physical manifestation of the energy fluctuations in the field. Detecting the Higgs boson would confirm the existence of the Higgs field and validate the theory of spontaneous symmetry breaking. In 2012, a crucial piece of this puzzle fell into place with the discovery of the Higgs boson at the LHC. This discovery was monumental. It confirmed the existence of the Higgs field and validated the theory of spontaneous symmetry breaking, providing a solution to the puzzle of gauge boson mass. And so, with one scientific breakthrough, the universe became a little less mysterious. The existence of Yang-Mills and the mass range of elementary particles remain a crucial area of research in physics. Peering into the future of Yang-Mills and the mass range, we see an arena ripe with potential for discovery. The importance of understanding this theory and the mass of gauge bosons cannot be overstated. These concepts are the threads that weave the tapestry of our universe, underpinning the fundamental forces that govern the cosmos. The Yang-Mills theory, with its gauge invariance and its association with the mass of gauge bosons, is a critical piece in the jigsaw puzzle of the quantum field theory. Each discovery, each piece that fits, brings us one step closer to a more complete picture of our universe. The groundbreaking discovery of the Higgs boson at the Large Hadron Collider was a significant step forward, providing evidence for the theory of spontaneous symmetry breaking. This theory elegantly solves the Goldstone dilemma, allowing gauge bosons to have mass without breaking gauge invariance. However, the journey of discovery is far from over. The field of particle physics is teeming with ongoing research, from probing deeper into the properties of the Higgs boson to exploring the potential existence of other particles. Each new finding, each unexpected revelation, opens up new vistas of understanding. And what of the mass range of elementary particles? This too remains an area of intense study. The question of why particles have the mass they do, and how this mass is distributed, is a key part of unraveling the mysteries of our universe. The path ahead is filled with exciting possibilities. With every technological advance, with every new experiment, we inch closer to a deeper understanding of the Yang-Mills theory and the mass range of particles. Each step forward brings new challenges, new questions, and new opportunities for discovery. As we continue to unravel the mysteries of the universe, The Yang-Mills theory and the mass range of particles will continue to guide our understanding of the fundamental forces that shape the cosmos.